So we have yet another example. And we want to calculate the reaction at A, which is fixed, and at D, which is pinned, and calculate the tension in cable CD. Okay. One of the most important things you can do is start noticing those two force members. Because the beauty of the two force member is if I am in tension, CD, and I am at a 3 to 4, then that means I am pulling back on that node just like a truss, okay? Which means my reaction at D has to be pulling back equal and opposite all the way through. So here's my vector line. And when I look at dx, I know that it is 3/5 of CD. When I look at dy, I know that it is 4/5 of CD. It runs with the same components that the vector runs, same xy components. Same thing down here. We have to be pulling back in tension, CD. So I'm going to have CX, which is CD times 3/5, and CY, which is 4/5 times CD. So it's like looking at a truss. If we can isolate these two force members, it really saves us a lot of heartache. Okay, two force members. So let's just go ahead and start overall. Overall, I have a free body diagram, and we're going to come across, and when we're looking overall, we ignore these internal pins, because when I take it apart, I show equal and opposite, whichever way. Put it back together, I don't see anything. So I have an unknown force here, AX. I have an unknown, AY, and I have an unknown moment at A. It is fixed. I have an applied moment of 25 pound-feet, 4 feet over. I have this pin at 2 feet over, and I have 100 pounds applied, 8 feet, 2 feet, cable going up, dx, dy, 3 feet, 4 feet. Okay, so when we start to look at this, we can see that we have 1, 2, 3, 4, 5 unknowns. Okay, we have 5 unknowns, but we don't really have 5 unknowns because we know the relationship between dx and dy. They have this relationship with this tension cable, and they are both a function of that tension. So really, we could say we have the unknown tension and these unknown forces over here at the wall, which is 4 unknowns. I only have 3 equations of equilibrium, so I have to start somewhere. If I start here on the left and I take it apart at B, I unscrew it, and I'm just going to look at A to B, then I'm going to have that internal force at the pin that I have to show. Plus I have all of this going on at the wall. So if I try to sum my force about the pin to just isolate, I'm going to have an unknown AY and an unknown MA that's creating a moment about that pin. I just don't have enough. I just don't have enough equations of equilibrium. So what if I start here from B to C? And if I start here from B to C and draw my free body diagram, okay, so I have my free body diagram of B to C. I have 100 pounds coming down. I have this tension cable, CD, coming up at a 3 to 4. And at the pin, I have BX, BY. It doesn't matter how I orient them because I can always change them later, but right now I've just got to get something on paper. 8 feet, 2 feet. So now when I come back and look, okay, this is doable. I do have enough equations of equilibrium this time. I can solve. I can start my solution. So looking at this, we can sum our moments about B. Okay, so I get a negative 100 times 8 plus well, I don't know this vertical, like perpendicular distance back down. That's too much math, but I know that this tension cable breaks into X and Y, just like a truss component, like any 2/4 member. And the X component has to be 4/5 of CD. So I have plus 4/5 of CD times 10 feet equals 0. So I'm going to isolate CD, bring this over, divide by 10 and multiply by 5/4. So we have 800, which becomes positive, divided by 10 times 5 divided by 4. And I get, that doesn't look right. Let's recheck this. So I have 800, okay? And then I'm going to divide that by 10, or multiply, okay? And then I'm going to multiply by 5 and divide by 4, and I get that the tension in CD is 100 pounds. And that's in tension. I assumed it in tension. It told me it was in tension. It's a cable. A cable has to be in tension. Cables don't work very well in compression because they're like here's a cable. Okay, it's not compression. It has to be in tension. Okay, so I have, this is now 100 pounds. And I can go back and look at my relationship that if my tension is 100 pounds, then I'm pulling at 100 pounds in tension on this joint at D, so I can very easily calculate dy and dx. And again, that's the beauty of a two-force member. If I had any other forces on here, it is no longer a two-force member. If I just have forces at each end, then they are going to act through, okay, through that longitudinal axis, and they are going to have components that break up. So if I look at CD, and I now go back and isolate that joint, so now we can look at joint D, just like we would with a truss, then I can say, well, dx equals 3/5 times CD, which is 60 pounds. And it's going to the right, just like I assumed. And dy is 4/5 times CD, which is 80 pounds, going up, dy. Okay, so I like to go back and just keep adding these things to my free body diagrams because it helps me kind of figure out what it is that I need to solve for next. So let's look at this overall. So now if I look overall, I could look at my overall picture, and I could sum forces X, sum forces Y, sum moments, and calculate everything here. My other option would be, I could look at, okay, this pin here at B. I know that it acts equal and opposite. Here's this applied moment of 25 pound-feet. AX, AY, moment at A. So I have lots and lots of options here. So many options. So what I'm going to do is I'm going to calculate my pin at B, transfer that force through, and just look at this little tiny nub from A to B. Okay, so let's continue with our free body diagram of B to C. And when I do that, I'm going to sum forces X, and I have a negative BX plus CX, and that was 60 equals 0. So BX equals 60 pounds, and if CX here is pulling to the right, it makes sense this is pulling back to the left. So I don't need to change anything. And then I can sum forces Y, and I have BY minus 100 plus, well, CD is in tension pulling, plus 4/5 of CD, or plus 80 pounds, it's the same thing, equals 0. And I find that BY equals 20 pounds, and it's going up in the direction that I assumed. So it has to be going down when I look over here at A to B that's isolated. Okay? And that's the thing, is you can't start mixing up everything that's happening here and trying to put it on this part of my free body diagram. If I draw an overall free body diagram, it only includes the things that I'm putting onto my system and the reactions that occur. once I start breaking it down, you've got to get your Post-it notes out. And if I'm looking at B to C, I'm literally just looking from B to C. I have to include everything on that member and the pins at B and C, but I don't include anything else because I've already taken those into account. If I'm looking at my cable CD, if I'm looking over here, okay, I don't include anything but what's on that picture. So get your Post-it notes out. So now I can look at this little tiny piece over here from A to B. So here's my free body diagram from A to B, and I can sum forces in the x direction, and I have AX, okay, plus 60 equals 0. Okay, so it pulled back on this piece, pushing forward here. They have to be equal and opposite. So AX equals negative 60 pounds. So AX equals 60 pounds pulling to the left. And I can sum forces in the y direction. And I get AY, okay, going up, minus 20 equals 0. So AY is a positive value, 20 pounds, in the direction I assumed, going up. And now I can sum the moments about A. And I have that moment that occurs at A. I'm going to come across, minus 25, okay, minus 20 times 6, and all of this has to equal 0. Bring the negatives over. The moment at A is 145 pound-feet in that counterclockwise direction that I assumed. Okay, and so that's the answer I get. Well, how can I go back and check all of this? How do I check? To check. How about we check by looking at the overall picture and we sum forces in the x direction of our overall picture. I have 60 going to the right from dx, and I have 60 going to the left, okay? So it actually went back to the left over here at A. 60 to the right, 60 to the left. So the sum of my forces in the x direction indeed work out. And some of you may be asking, wait a minute, Professor Emerson, but I am only applying a vertical force and a rotation. And that's true. Well, how did I get this x value? Okay, it's because I have this cable. Anytime you introduce a member that is acting at any different angle besides flat, okay, besides flat, like these, then you're introducing the x component. As this tension in the cable is pulling down at D, I have to be pulling back equal and opposite. And if I'm pulling back equal and opposite, I am developing both x and y components to pull back. So I end up with, it makes sense, the wall is having to pull to the right to keep this cable in place. As I'm loading this and putting this moment, this system's going to want to come down and to the left, to the right. So it makes sense that at AX, I'm having to pull back to the left to keep this system in place. Okay, to keep this system in place. We can also sum forces in the y direction, and they should equal 0. I got for AY, I got 20 pounds going up. And over here for DY, I got 80 pounds going up. And I have an applied 100 going down. So 20 minus 100 plus 80 indeed equals 0. Okay, now I need to go back and check this moment. I got a moment of 145. This is 80, this is 60. So let's sum all of our moments up. Sum of the moments, and let's just do it about A. It doesn't matter. I have a 145 moment at A. These don't count. I'm going to subtract a 25 applied. I'm going to subtract the moment created by this 100 pounds, which is 8, 9, 10, 11, 12, 13, 14 feet. Okay, and when I look up here, I have an x component. Okay, it would create a negative minus 60. Its distance, perpendicular distance, is 4. I also have this y component. It would be causing a positive moment, plus 30. And its total distance is 4, 5, 16, 17, 18, 19. So we have 19 feet. And all of that nonsense, it's got to equal 0. 145 25 minus 114 times plus 60 4 times 19 30 times. Whew. And I have screwed up somewhere. Okay, I've either messed up this equation or I've messed up something. So I have a 145 positive minus 25 minus 100 times 14 minus 60 times 4 plus, oh, it's because this is an 80, not a 30. I don't know where the 30 came from. Let's make this an actual 8. And now let's try again. 145, 25 plus 100, 14 times plus 60, 4 times plus 80, 19 times plus. And I get 0 equals 0. Check, smiley face. Okay, so I didn't have that 0 equaled 0. And that quickly told me I've messed up somewhere. Either I have messed up this equation, which I did. I had a 30 instead of an 80. Or I've messed up somewhere else. It takes 2 seconds to check your work. But it will ensure that you always have 100% correct answers. Okay, it's just a good habit to get into. Does it make sense is the other question. Does it make sense that I have X components on my system? Yes, I have a cable pulling down. I've got to be pulling up and to the right to balance out that cable. If I've introduced an X, I've got to have an X. Okay, so the whole thing behaviorally is going to want to come down, and I've got to be pulling back up this direction to keep it up on the wall.